Hi everybody, my name's John Downing. I'm a professor of limnology and aquatic ecology. Today I want to talk about the light environment in aquatic ecosystems. I have three simple objectives for this discussion. First, I want to teach you something about the importance of light quality and quantity in aquatic ecosystems. It varies quite a lot depending on what kind of system you're in, and that matters quite a bit. Next, I want to talk about what blocks light and alters the color of it, because the quality of the light, or the color quality of the light, is also very important for the functioning of especially primary producers, or things like algae and aquatic plants. And then we'll talk just really briefly about how light penetration is measured. So light is basically the driver of ecosystem processes. It, in fact, alters the heat budgets and stratification of lakes. It also is the source of photosynthetic energy, whereby plants make a profit and create food and energy resources for other organisms that live in aquatic systems. And also, a sort of a negative importance of light is its ability to cause ultraviolet damage to organisms, especially in surface waters or in the surface film that we talked about, that exists because of that high surface tension. And also they tend to drive light tends to drive predator-prey interactions because of the visual cueing or the ability to search, the need to search for prey, and also to give visual cues to conspecifics, or organisms of the same species. So basically the light environment is as important to aquatic ecosystems as it is to terrestrial ones. In fact, in many ways, more important, because it's a rarer commodity. So here's how aquatic plants make a profit. And you've probably seen this equation a bunch of times. Over here on the left you have 6 carbon dioxide molecules, and obviously we have lots of water in the aquatic environment, so we have 6 water molecules. And in the presence of light, these photosynthesizers, such as this diatom, green alga, cyanobacterium, and so on, in the presence of light, they can turn that CO2 into sugars, or basically other sorts of carbohydrates or energy stores, and in the process they generate oxygen. And now one thing you're seeing here for about the first time in this course anyway is the reciprocal nature between carbon dioxide and oxygen. Those things that take up carbon dioxide usually give off oxygen, and those things that use oxygen usually give up carbon dioxide. So there are pigments, various pigments that make up that photosynthetic apparatus that you see here in the center of this image. You can see those pigments are different colors, and in fact, different kinds of plants have different sorts of photoreceptors or photosynthetic pigments. Now, probably the one that you're most familiar with would be chlorophyll. Basically, all photosynthetic plants contain chlorophyll A, B, or C1 or C2. The higher plants in green algae, that is to say the chlorophyta, really rely on the various chlorophylls. Very important, that green sort of pigment that gets lost in the fall. Well, one pigment that you see in the fall after the chlorophyll goes away from the trees are the carotenoids, and these are very orangey, yellowy materials, and there are 15 different carotenoids. And you can see I have a carrot there because not really a joke, because the carrot has a lot of carotenoids in it, and these tend to be more important than chlorophyll in pretty much all kinds of algae, except for the chlorophytes, the cryptophytes, and cyanophyte, or the cyanobacteria, and the rhodophytes. Next, another really important kind of photosynthetic pigment would be the biliproteins, and sometimes we call these cyanoproteins or cyanopigments, and these are predominant pigments in the rhodophytes, cryptophytes, and in the very important cyanobacteria. Now, the importance of all this is that different pigments use different colors of light. Here you see the wavelength of light on the x-axis, and that signifies the color of that light here, moving from violet to blue to green to orange to red. These different wavelengths are absorbed. This is an absorbance spectrum. This is the green one, the bright green one, is the absorbance spectrum of chlorophyll. And you can see chlorophyll has two peaks in absorbance, one here up around 400 something nanometers, and another one way up here at about 680 nanometers. And in fact, when we're measuring the fluorescence of chlorophyll, this is where we measure it is right up around 680 nanometers because it absorbs so well there. Now here's the carotenoid spectrum. You can see that they're absorbing light in a different place, of a different color than the chlorophylls are. And some of the bilirubins are signified by this sort of blue-green plot. And this shows that those kinds of photosynthetic pigments are found in have absorbance spectra that accentuate a completely different color of light in the greens and oranges. You can imagine that if you're a phytoplankton or an algal cell, it does you very little good to have a lot of light of a color that you can't use. And so clearly the wavelength of light and the absorbance of different wavelengths of light by water is very important in determining which kinds of organisms can make a profit. Now here are some terms pertaining to photosynthesis, first is PAR. This is the acronym for photosynthetically active radiation. This simply means the color spectrum that can be used by the photosynthetic apparatus of plants, and this is approximately 400 to 700 nanometers in breadth, and this we refer to as PAR, or photosynthetically active radiation. Another process that we refer to, and a term that you should know, is photoinhibition. This means you probably noticed sometimes sound is too bright for you, loud for you to be able to hear well or clearly. Sometimes you can get too much of any kind of stimulus, and the same is true for light. You probably have noticed this also. Sometimes when the sun is extremely bright and you're trying to drive, your eyes simply don't work terribly well because they're getting overloaded with light that they can receive. Photoinhibition is the inhibition of growth or function of organisms by having too much light in the spectrum that they use. And in fact, even short wavelengths, even small amounts of short wavelengths can damage cells very severely. So photoinhibition means that there's too much light, and so that it inhibits production or inhibits function rather than enhances it. Another term you should learn is the photon flux density. This is a rate at which photons hit a surface, and this is usually measured in moles per square meter per second. This is one of the ways, one of the kinds of units in which we measure light flux. Now, plants use visible light with wavelengths from about 400 to 700 nanometers. Well, what does that mean? Let's look at this on this graph. This graph breaks out for the 400 to 700 nanometer range, and this is from the new version of the CALF text. You see that this is the purple through red colors are used quite effectively, and this is the visible range of light, and also this is the photosynthetically active or available radiation. Below that, at lower wavelengths, we find ultraviolet, which is very damaging, and above that we find the infrared, which are basically absorbed and expressed as heat. So plants use visible light with wavelengths from about 400 to 700 nanometers. Now, solar radiation is received at the Earth's surface. It's different from the solar radiation received by the extraterrestrial atmosphere, meaning outside the Earth, not where extraterrestrials live, obviously. On this dashed line shows the frequency, or the frequency distribution of solar flux at the extraterrestrial. This is the extraterrestrial solar radiation, and this solid line shows the amount of energy and its energy spectrum, or the wavelength spectrum received at the Earth's surface. So this is at ground level. And what you see from this graph is that there's quite a lot less radiation at the ground than there is hitting the outer atmosphere. And this is because things like ozone here will absorb radiation, also oxygen, and water vapor is very good at absorbing radiation at a variety of frequencies. Out here to the right, of course, is the infrared, or the heat spectrum. Down here is the ultraviolet, and you see ozone. Ozone here is very good at absorbing the ultraviolet, which is why we're trying to preserve this ozone layer to protect us against harmful ultraviolet rays. But the spectrum of energy received at the Earth's surface is quite different from the spectrum of energy that is first received at the outer parts of the atmosphere, due to absorbance by a variety of different substances, including oxygen, water, and ozone. Now, likewise, you see that water is quite good at absorbing radiation, especially up in the infrared and at various wavelengths. So you can expect that as that as that light hits a water surface and begins to penetrate into a lake, that many changes occur. Here, for example, we see the quantum irradiance here measured across a variety of different wavelengths, and these are the wavelengths received at the Earth's surface in a bunch of different places. Here is the quantum irradiance and frequency distribution at Crater Lake, Oregon, which is very high. It's at high altitude, so it has a much higher quantum irradiance. This is the quantum irradiance received at the Gulf Stream in the Bahamas, and this is at a lower altitude, very with much more sort of absorbance above it. This is the San Vicente Reservoir in California, and it's a spectrum of photosynthetic energy. This difference in overall light flux from an average of something like 2,500 times 10 to the 15th quanta per square meter per second per nanometer, it is much different. It varies by almost the double as we go to higher altitude. So you can imagine that altitude has an effect on the overall irradiance received by any aquatic system. Now here's the global radiation in the northern and southern hemispheres as a function of month. We saw a similar sort of thing when we looked at temperature. The temperature distribution throughout the year, it follows a great deal these same sort of sinusoidal relationships, because, of course, light and the associated infrared radiation is one of the things that heats these aquatic systems. So basically what you're seeing is different latitudes over here, and in the northern hemisphere and in the southern hemisphere. You can find where you are, and this will show you just about how light flux varies. It's a very sort of regular sinusoidal pattern that varies monthly. Now, this is a question that is often missed on exams, and one that you should pay some close attention to. If we ask ourselves what determines the radiation received by a lake, we already know that that direct solar radiation is affected by what goes on in the atmosphere. But a lot of other things happen to it after it hits the surface of a lake. Basically the net radiation surplus, or the amount available to organisms for photosynthesis and other processes, are affected positively by a variety of different things, by 3 different things, and negatively by 3 other ones. And these are things that you should remember. That the direct solar radiation has added to it the indirect scattered and reflected radiation from sky and clouds, which can be quite considerable. If you know, for example, that you can still get a suntan pretty well, even if it's cloudy, that's because not all the UV is filtered by water in the clouds, but also you get some backscattering from areas where the scattered and reflected radiation from the sky and from the clouds. So some of it is coming down toward the Earth, other than the simple direct solar radiation input. Also added to that is the long wave or infrared thermal radiation from the atmosphere and topography. There's a back radiation of this. Let's say at the nighttime or in the evening, you're still getting radiation or thermal radiation coming off of land surfaces, and clearly the opposite, that you get some from water surfaces back to terrestrial systems too. So there is some thermal radiation from the atmosphere and topography. So those are the various 3 sources that determine the radiation surplus, or the amount available to work with in an aquatic system. Now, taken away from that would be the radiation reflected from the lake. And you have probably seen how much radiation can be reflected from a lake. If you've ever watched one in the evening, you get the glittering of the lake that reflects a substantial amount of radiation back to your eye. Another factor that's taken away from the radiation received by any kind of organism in the system is the radiation scattered upward and lost. This would be through reflection as the water passes through the water. As the light passes through the water, there's a backscattering and upward loss of radiation. And then, of course, there's a loss of radiation from the emission of long-wave radiation, essentially the equivalent to Q sub A above, but from the water. So there is a loss of that radiation away from the lake. So for an organism within a lake, that net radiation surplus is affected positively by direct solar radiation, by indirect scattered and reflected radiation from the sky and clouds, from long-wave thermal radiation from the atmosphere and topography, and affected negatively by radiation reflected away from the lake, radiation scattered upward and lost away from the point of reception of that radiation, and the emission of long-wave radiation from the system. Now, we might ask ourselves, you've looked at probably a lot of ecosystems in your lives already, and you probably, when you were a child, you probably usually colored water blue, but you probably also noticed that it doesn't always look blue. And certainly at the right-hand side, you can see a bunch of systems where the water doesn't really appear to be blue. Now, if you drop all materials from the water, all kinds of particles and dissolved substances, the water will in fact absorb most radiation other than blue. And then if it gets reflected back to your eye by a white surface, then the water will look to your eye to be very, very blue indeed. Now, also, when you look at a lake, look at the lower panel there, I guarantee to you that lake was not terribly blue itself. The water wasn't blue. But what you're seeing in that image is reflection of sky color back to the eye of the observer, or in this case, to the camera. Also, you can dissolve material in water, and the dissolved substances tend to color that water in different ways. The middle image shows a lake that looks very pink. Now that's not due to the water being pink itself. That's due to red material in the water reflecting that light back up to your eye. But you can dissolve, just like a cup of tea or a cup of coffee, you can dissolve material in the water, and dissolved substances tend to give the water their color, and that is what we call true color, because if you filtered all the particles out of it that would have some color to them, then that would be the color that it would have to your eye. That's the clear liquid. And in fact, many of the lakes that we look at in northern climates are quite brown in color, even when you filter out the particles. Now, another thing changes the appearance of water due to light, and those would be suspended particles. Things like glacial flour and marl and sediment particles and algal particles. Those suspended particles reflect light back to your eye, accentuating the true color if they're white, but also giving their own apparent color to the water by the color of those particles. So apparent color then is how the appearance of the water color is altered by processes or substances that are suspended, not due to dissolved materials. So true color is from dissolved substances, and apparent color is due to suspended particles normally. Now, in the case that the suspended particles are white, then the color is going to appear to your eye to be the color of whatever is dissolved in the water. Other particles exist in water, and these would be algae and purple bacteria. You see those in the middle. In Pink Lake in Australia, there are purple sulfur bacteria. You also see green particles in the lake at the top that will reflect back their color to your eye, and these will alter the perceived color or the apparent color of the water. And finally, bottom color. Often in places like the Bahamas or the Caribbean, the bottom of the lake, bottom of the sea is quite white, and the water is quite clear. So it will reflect back to you the true color of the water, which in fact looks to be blue because of the light absorbance characteristics of water. So what determines the radiation received by the cells? Well, it's the water itself absorbs some kinds of radiation. Dissolved substances like coffee or brown stuff block and filter radiation, and then suspended particles block and absorb radiation, such as you'd find in milk. The little particles of material that are suspended in that milk will also block and absorb radiation. So there's quite a gauntlet for light to have to run before it actually gets to a cell so that it can drive photosynthesis. It can be filtered out by water itself, filtered out by dissolved substances, and filtered out or reflected back by suspended particles like sediment and, well, not milk, but various kinds of particles that are suspended in the water. So here are some terms pertaining to light penetration. Now, when we talk about the clarity of water, we usually talk about transparency. Now, transparency is the combined attenuation of light by scattering and absorption by water, by dissolved substances, and suspended solids. So anything that can block radiation then alters the overall transparency. And transparency is essentially what allows you to see the bottom, or to see your feet, or see fish underwater. The higher the transparency, the clearer the water, and the easier it is to see through it. Now, there's another thing called turbidity, and you have observed turbidity probably if you've had a glass of milk and drank or poured out most of the milk and then filled it with water. That cloudiness of the water is called turbidity, and that's light scattering and absorption due to organic or inorganic suspended matter. So if you add particles, let's say you add a little bit of flour to some water and shake it up, you're going to suspend some of those particles in the water, and you're going to make it turbid. If you filter out those flour particles, you haven't changed the color of the water that is resulting, so you have not changed the true color, but you have altered the turbidity. Now, another term is color, and we've already talked about true and apparent color, but let's review it. Color is it can be due to dissolved organic matter that absorbs shorter wavelengths, shifting light toward yellows and reds. And this is the example you can use for yourself is basically a tea bag put in water. You have put some organic matter into the water, and you've shifted light toward yellows and reds. Now, true color is the color caused by dissolved substances. So tea would be one of those examples. Also, putting red food coloring into water would change its true color because it's dissolved. So true color is color caused by dissolved substances. Now, apparent color is caused by particles and substances together. So usually apparent color, when apparent color differs from true color, it's because of the addition of some sort of particles. Now, we measure light quantity using a variety of different words and ideas. One is transparency, and that's the overall ability of light to pass through water body. And this is integrated transparency, and is usually measured with a Secchi disk. And I'll show you how a Secchi disk works in just a second. Turbidity is measured by turbidimetry, and this is based on light scattering. And just basically how this works is you shine a light into the water and then measure what's scattered back toward the source, and that will give you a measurement of turbidity. Color is often measured by comparison with platinum cobalt standard series or spectral absorbance at about 440 nanometers. This will, and this is on a filtered sample, so that you can actually see the true color of the water. And then light penetration is often measured with a submarine photometer, and we calculate a thing called the extinction coefficient, which is extinction not of organisms, but extinction of light. And we can calculate how long it takes to, how much water must be penetrated before most of the photosynthetic energy is missing. So here's a Secchi disk. It's a very elegant and historic tool used in the aquatic sciences. And this is a means of measuring overall transparency. You can make a disc like this yourself from an 8-inch pie plate covered with paint or covered with sticky plastic shelf liner or something like that. You lower it down into the water over the shady side of the boat on a line or a piece of rope until it just disappears from view. Then you read that depth from the calibrations on the line. Next, you bring it up slightly until it just comes back into view, and you take that measurement, and then the average of those two measurements is recorded as the Secchi disk transparency or Secchi disk depth. This gives you a very good estimate of about the 95% extinction depth of light, and it will tell you something about where it gets dark in an aquatic system. It's about at the Secchi disk level, although your eye can see something at that level, but most plants will not be able to actually make a photosynthetic profit. So the Secchi disk transparency, and you may think that this has a lot to do with how much light's available at the surface, that the measurement that you'll get will be quite dependent on time of day, and this really isn't true. And here's an old graph showing I sub O, which is the incident radiation. That's the amount of radiation hitting the surface of the lake, and you can see it's decreasing as it gets later. This is 8 o'clock and this is 10 o'clock at night. And I think you can see quite well that the measured Secchi disk transparency varies extremely little. Here it's measured in centimeters, actually in meters, which is, well, centimeters is 100th of a meter. Stays very stable at just under about 3 meters depth. until it gets quite dark at about 8:45, 9 at night. And then it begins to decline as it gets darker and darker. But remarkably, your eye is so adjustable to light levels that the Secchi disc transparency stays very constant as light level changes. Now, we use quantum sensors to measure the photon flux density, or the actual flux of radiation into an aquatic system. And there are a couple of parts to these, and this is a kind of an old picture of them. But here's this is called the deck cell, and this is it's a photocell that you keep on the deck of the boat, or keep it in the boat, so that you're measuring the actual incident radiation at the surface of the water. Then you have an array like this in sort of a T, with one quantum sensor pointing upward and one quantum sensor pointing downward. And this measures the downwelling radiation and the upwelling radiation, that is to say, the amount reflected back upward. And both of these are important measurements that we make, although probably the one that we rely upon the most for estimating things like the extinction coefficient would be the downwelling radiation. So the upwelling light is also important, but mostly we look at the downwelling radiation and look at it sometimes as a percentage of that received by the deck cell as we lower the quantum sensor down through the water column. So when we're making measurements like this, and these are hypothetical measurements, but not unlikely ones for us to see. Here we have the depth on the y-axis going down to almost 20 meters, and the light intensity, which is a percentage of that received by the deck cell. And so you can see just under the water surface, we get, 75, 80% of the irradiance is available. But as we go down through the water column, that light decreases and decreases and decreases until there's very little light at about 18 or so meters depth. Now, what this looks like a very smooth graph, and we do see smooth graphs like this very frequently because the upper mixed zone of lakes tend to be fairly homogeneous, and so you don't have various little layers you're going through. So if we take the logarithm of one of the axes of those data in the previous plot, you find that it's a fairly straight line, and we frequently do find this. Now the slope of this line in log terms gives us an estimate of the percentage of radiation that is lost per unit depth. And this is a homogeneous lake, and the extinction coefficient is calculated as at right by simply rearranging this very simple equation, which expresses this linear relationship between the percentage of light at the percentage of light at depth as a percentage of the light at the surface. Now, in some lakes, however, we may find non-homogeneous situations, and what you can see here is that the light at the surface is decreasing much more rapidly as it is down deeper in the water. And we frequently will find this, that in the surface layers of lakes especially, we'll find much more suspended particulate matter, things like algae and other particles in the surface mixed zone, where that just above the epilimnion. And then as we get deeper, sometimes lakes will get clearer. And so here we have a clearer system. You can see that the light intensity is not decreasing as rapidly with depth as it was over here. Light attenuation is also a function of turbidity and color, and so here we see a bunch of those kinds of plots as we saw in the previous graph for a bunch of different sorts of lakes in the world. Here's a percentage of incident radiation and the depth, and we see this for places like Lake Chisholm, Toombs Lake, Lake Perry, Crater Lake. We know Crater Lake is a very, very clear system. It has almost no nutrient in it. And look at how much of the incident radiation is still left at fairly substantial depths, whereas Lake Chisholm loses almost all of its light. It's down to 1% irradiance before it even gets to 1 meter. And you can guess from that that there's a lot of material suspended in that water. And Lake Chisholm is a eutrophic system that has a lot of nutrient and a lot of algae. We also measure the spectrum of irradiance. We've talked quite a bit about that over the last little bit. On the left-hand side, you see a handheld submarine spectroradiometer. And this is a piece of equipment that can tell you the color spectrum of irradiance received at various depths. On the right-hand side, you see an old photo of a similar kind of unit that is lower down in the water. And this gives a scan of the distribution of wavelengths at depth and tells you what the relative color is, color distribution or wavelength distribution is at various depths down in an aquatic system. So water does alter this spectral composition of water, and I think what you see here is the average percent transmission of varying kinds of water over a variety of different light spectra, going from down in the violet up to the red in that PAR region, that photosynthetically active radiation region. Pure water absorbs very little in the blue, green, and violet, but quite a lot in the yellow, orange, and red. And that's why if you're looking through a column of very pure water, distilled water, the Caribbean, Lake Superior, other beautifully clear systems, the water itself will look pretty blue. Now, if you move into places like Lake Victoria and Lake Kariba that have more materials in them, both dissolved substances and suspended substances, the average percent transmission in the blue region declines pretty fast. And if you look down here at Lake Bangweulu, that has a lot of dissolved substance in it, the absorbance of the violets and blues are almost complete. So that water will never look blue to your eye if you're looking through it, even if all the particles are taken out of it. It will tend to look much more in the sort of the yellow to, well, green to yellow to brown, depending on the intensity of absorbance and the exact kind of material that is dissolved there. So water and its composition alters the spectral composition of light, as well as the percentage transmission. Clear water transmits a lot of light, pure water does, and that with dissolved substances has a much higher extinction coefficient. You can see that basically from these photos. The photo at the top is from an ultra oligotrophic lake. This is from Lake Tahoe, a photo under the water, and I think you can see, at least to your eye and to the camera, the water looks pretty blue. Now, at the bottom is lower left is an artificially eutrophic lake showing the spectral composition of light at depth. And you can notice two things from this, comparing it to Tahoe. That one thing you notice is that there is very little energy available, even at very shallow depth. The little bump down at the bottom is 3 meters depth. Compare that with the plot from Tahoe. The other thing you could notice from that is it's shifting the light spectrum much more to the right in a eutrophic lake than in an oligotrophic lake, because of the dissolved material in it and the particles reflecting that light backwards, back up out of the system. The water will tend to look much more sort of yellowy green, as you see in the photo at right. The photo at right is actually lower right is from a mesotrophic lake, not a eutrophic one. So you still have enough clarity there, but you'll notice that the cast of the water is much more greeny yellow than it is bright blue, and that's because of the absorbance of light by the water above, including dissolved substances and particulate matter. Here's the extinction of various colors of light in distilled water on both a linear and a logarithmic scale. And what I'd like you to see from this is that red, it becomes extinct much more rapidly, and orange has much lower extinction than. Sorry, I keep getting this mixed up, but let me start over again. What you'll notice is that there's much that red disappears much more rapidly from the water column. This is the depth of the water here, and orange and yellow all disappear much more rapidly than does blue, and blue has a great deal more of a greater percentage of incident radiation than you would see than you see for the red, orange, and yellow. This is in pure water. It's quite different, of course, when you look at real lake water, that oftentimes the blue will have a fairly high extinction coefficient compared to the other colors, such as reds and greens. And you see the equivalent plots to the right-hand side showing you that basically the color extinction of colors has inverted in this real lake water. Depth influences light quantity and quality, and at the left-hand side, I just like to. This is a light spectrum taken from some work by Wetzel and Likens, and you're seeing sort of microwatts per square centimeter in radiation across a variety of different wavelengths. And again, the blues and violets will be to the left, and the orange and red will be to the yellow, orange, and red sort of to the right. And what you can see, I think, from the y-axis is that there's at 1 meter depth in this lake, there's very much more radiation available than at 20 meters depth. Just a tiny fraction of it left at 20 meters than that you would see at 1 meter. And the other thing you should note is you've shifted the light over to the right in much more closely into the absorbance spectrum that would be useful to something like a cyanobacteria, because the bilirubins sort of absorb in that range, although the chlorophylls also are absorbing at up above 600 nanometers, which is where the light is most abundant, is from about 550 to 600 nanometers. So the light quality and quantity both change with water depth. Light quality changes with depth and water color, and here we see some various lakes, again the same kinds of irradiance spectra with different colors across the x-axes, and the same y-axis is shared by all of these graphs. Clearly, Toombs Lake has a much greater light extinction than does Lake Perry, and Lake Chisholm. Dissolved organic carbon also rapidly attenuates ultraviolet light, and this is important for removal of this ultraviolet. In this plot, you'll see the percentage of UVB irradiance that is you see how far you get down in the lake before you get 1% UVB penetration, and so. Clearly, if the dissolved organic carbon is quite high, the depth is very, very low, and most of the UV is lost in the very first centimeters of that ecosystem. Well, whereas if the dissolved organic carbon is quite low, that would be the tea-like substances, then some ultraviolet can in fact penetrate a little bit farther into the water column. So to summarize for session 5, which is our discussion of light, we know that light provides energy that drives all aquatic life, and so it's very important, if you're going to have positive production, to have substantial light. The amount and color determine the production, as well as the algae community structure, and also the community structure of the aquatic macrophytes. Light also determines where you will have vegetation actually growing on the bottom, because in order for that to happen, light has to penetrate all the way to the bottom. The light climate is altered by all kinds of things, but by backscattering, and don't forget how many factors there are that alter the net amount of radiation absorbed by that's absorbable by a phytoplankton. The light climate's altered by absorption by particles and by dissolved substances, and also by backscattering and reflection and re-radiation of energy. Finally, there are many different important measurements of light. They are things like transparency, turbidity, color, and extinction, and these are the things that limnologists measure on aquatic systems in order to determine how much light is available to organisms for creating primary production.